Hello everyone, welcome to my class. Slowly we are approaching towards the end of this course, and today we are going to start the last module, module 12 of this course. In this module, we will learn about anti-reflecting coating, which would be followed by basic concepts of holography, then basic concepts and ray optics consideration of optical fiber, and ultimately we will be introduced to lasers. Today we will start with the first topic, which is anti-reflecting coatings. Now, in optical instruments, we know that whenever light falls from air to a glass surface, there is roughly around 4% of reflection. And any optical instrument like microscope or telescope, it has a series of lenses, sometimes 5, 6, 7. Now, if you consider 4% reflection from each surface of the lens, then the total light which is lost in reflection would be too much, and therefore, we will have to design the lens surface in such a way this reflection loss reduces down to a minimum. Okay. And one of the important applications of thin film interference phenomena lies in reducing the reflectivity of lens surface. We studied this thin film interference in a great detail while covering the interference part of this course. Now, using that knowledge, we will try to develop an anti-reflecting coating which reduces the reflectivity of lens surfaces. Now, when a light beam which is propagating in a medium of refractive index n1 is incident normally on a dielectric material of refractive index n2, the amplitudes of reflected and transmitted beams are related to that of the incident beam through certain relations, okay, and these relations are given here by equation number 1 and 2, where AR is the amplitude of the reflected light, AI is the amplitude of the incident light, and AT is the amplitude of the transmitted light. Schematically, we can draw it like this. This is refractive index of medium n1, this is refractive index of medium n2, and the light is incident normally, okay, and the amplitude of the incident light is AI. A part of the light get reflected and its amplitude is represented by AR, while a part get transmitted and the amplitude of the transmitted light is represented by AT. Okay. Now, you see that here this coefficient appears, this is called coefficient of reflection, and it is represented by small r. Small r is equal to n1 minus n2 upon n1 plus n2, where n1 and n2 are refractive indices of first and second media respectively, while this term in the bracket is called transmission coefficient or amplitude transmission coefficient. And we know, we have already studied about this T and R, they are Fresnel relations. Now, for near normal incidence, the reflectivity of the crown glass surface in air is around 0.04, which can be calculated from the same relation n1 minus n2 upon n1 plus n2, this relation, okay, and this therefore, the reflectivity would be 0.04. This means that 4% of the incident light is reflected. Okay. Similarly, now to reduce the losses, the lens surfaces are often coated with some thin film, and this thin film is chosen in such a way that the reflection from the upper surface and reflection from the lower surface of the thin film, it destructively interfere. What I mean by saying this is that, suppose this is the glass material, glass, and this is air. Now, on top of the glass, we coat thin film on the top of the glass, and the thickness of this thin film is chosen such that say this is the incident light, then there would be reflection from the upper interface, and this a part of the incident light will go within this thin film, and then there would be a partial reflection and partial transmission. Now, if these two light interfere destructively, or if these two light beams they are out of phase by 180 degree, then there would not be any reflected light. Yeah, there would be complete destructive interference, and there would not be any light. All the light will go in the transmitted direction. Okay. Now, to have destructive interference, we require path difference of lambda by 2. Yeah. Now, if the thickness of the thin film is lambda by 4, then from this figure we are seeing that the incident light is traversing through the thickness of the thin film twice. Okay, now you see that this light is falling here and then it is going inside, then getting reflected and then coming out. It means it has traversed the film thickness twice, and therefore, total extra distance travel would be 2 times lambda by 4, which is equal to lambda by 2. Okay. Now, if you take refractive index of the thin film also into the account, then the thickness of the film, it would be lambda by 4 into 1 by n, and here too n will appear in the denominator. Therefore, film thickness, to have destructive interference, film thickness should be equal to lambda by 4 n, and this is what is written here. To reduce these losses, lens surfaces are often coated with a lambda by 4 n thick anti-reflecting film. The refractive index of the film is less than that of the lens, because here in this calculation we did not take into account the extra phase difference due to reflection, and this only happens when the refractive index of this glass or the lens which is lying below, it is larger than the refractive index of the thin film, and the refractive index of the thin film is of course larger than that of the ambient material, which is air. Now, the same figure is drawn here in a more clearer way. You see that ray number 1 is falling on the interface, and then the reflected rays named as ray number 2, the transmitted rays named as ray number 3, the reflection from the lower interface generates a ray which is named as ray number 4, and then this ray number 4 transmit out into the air, and this transmitted ray is named as ray number 5. The material below is our lens, that and it is made up of glass, and its refractive index is taken as Ng. The anti-reflecting coating which is given by this thin film, this thin strip represents the anti-reflecting coating, and its refractive index is considered to be Nf. F stands for film. Okay, the refractive index of film is Nf, which is considered to be smaller than that of the glass. Okay, Nf is less than Ng, and the refractive index of air is taken to be Na. A stand for air. Okay. Now, here we assume the incident beam is normal to the interface of the medium. Okay. We always consider near normal incidence. Okay. Under this condition, the rays reflect back from the top and bottom of the film, and since that is wasted light, we would like those rays to emerge 180 degree out of phase and cancel each other. Okay. And if these two reflected rays are out of phase by 180 degree, they will destructively interfere, and then there would be no reflected light in the air, and this is how we can cancel the reflectance. We can make reflectance 0 and save the light, and then everything would be utilized better in the optical instrument. Now, for anti-reflecting coating, the film thickness is of prime importance, and this film thickness d, it should be such that the path length difference, that is 2 NFD, it is equal to lambda by 2, and whenever this condition is satisfied, we get destructive interference in reflected arm. Okay. And from this equation we can easily derive the expression for d, which gives destructive interference, and this d is equal to lambda by 4 NF. Now, consider the 3 layer medium. First layer is air, second layer is thin film which is of refractive index Nf, and the third medium is glass which is of refractive index Ng. Now, if A is the amplitude of the incident wave, then the amplitudes of the reflected and the refracted waves are minus NF minus NA upon NF plus NA into A. This would be the amplitude of the reflected wave and this would be the amplitude of the transmitted wave. Okay. And this relation we got from these equations, equation number 1 and 2 respectively. Yeah, because here the while calculating the reflected amplitude we used N1 minus N2 upon N1 plus N2 into A, okay, the incident one, but here N1 is air and N2 is film and the refractive index of air is smaller than that of the film. Therefore, air is, we take minus sign out and then write it as NF minus NA, yeah, upon NF plus NA. If you bring the minus in the inside the bracket, then it would be NA minus NF, which is N1 minus N2. But since NF is larger than NA, we want NF to be before, we want NA to be subtracted from NF, and therefore we are writing NF first and then subtracting NA from NF. Okay, and this is why N2 is coming earlier here in this formula, okay, because minus sign is taking care of this change. Okay. Similarly, for transmitted light it is 2 N1 upon N1 plus N2 and 2 N1 is NA, N2 is NF, yeah, it is clear, N1 is NA, N2 is NF, and this is how we can derive the reflected and transmitted amplitudes. Okay. And this is for ray number 2 and ray number 3. Yeah, reflected amplitude means the amplitude of ray number 2 and transmitted amplitude means the amplitude for ray number 3. Now, once it is done for ray 2 and ray 3, we calculated the amplitude. Now, let us calculate the amplitude for ray number 4 and ray number 5 as shown in this figure 1. Now, you see that ray 3 is falling on this interface and then it is getting reflected, and this reflected ray is named as ray number 4. Okay. And what amplitude falls on this interface? The amplitude of ray 3, and what is the amplitude of ray 3? It is given in this point. This is the amplitude of ray 3. Okay. Therefore, for ray 4 we will again write this formula N1 minus N2 upon N1 plus N2 into amplitude, and amplitude is 2 NA upon NF plus NA into A. Now, here N1 is refractive index of anti-reflecting coating layer. Okay. N2 is that of glass. Okay. Therefore, N1 is NF and N2 is equal to Ng. We will substitute this here. Now, you see that in place of N1 we will write NF, in place of N2 we will write Ng, okay, NF, Ng. But since Ng is larger than NF, we will take minus sign outside the bracket, this term would be plus, this term would be minus. And effectively, we will have Ng minus NF upon Ng plus NF into twice of Na, NF plus Na into A, and which is what is written here. Okay. Similarly, we calculate the amplitude for ray number 5, which is the transmitted part of ray number 4. Okay. Here we apply to Na upon N1 plus N2 and then the amplitude of ray number 4, and this will give us this expression. Okay. Now, for complete destructive interference, the ray number 2 and 5 they should be equal and in amplitude, but they should be out of phase by 180 degree. Therefore, the wave corresponding to ray number 2 and 5 should have the same amplitude. Okay. Let us compare their amplitude. Here on the left hand side we just put the amplitude of ray number 2, while on the right hand side the amplitude of ray number 5 is written. Okay. Now, we will simplify this. After simplification we get this expression. Okay. And while to reach at this expression we have used one approximation, and we say that 4 NF Na into NF upon NF plus Na whole square is nearly equal to 1. This we equated to 1, and after this we reached at equation number 6. Now, from equation 6, if you further simplify it, then you can clearly see that NF, if you calculate the expression for NF, then NF would be equal to a square root of Na into Ng. It means, if refractive index of film is a square root of refractive index of air into refractive index of glass, then this film will work as a anti-reflecting coating. Okay, this film will work as an anti-reflecting coating, and this technique of reducing the reflectivity is known as blooming. Now, notice that here we have done everything for a given refractive index, and we can treat refractive index as a constant as long as the wavelength of the light is fixed. Okay, the interrogating wavelength is treated fixed here. Okay. Now, if we change the wavelength, then this condition will not be valid anymore. Yeah, we will have to this condition would be valid, but we will have to change the refractive index accordingly, because refractive index is wavelength dependent quantity, but d, the thickness d of the film, that would be fixed once designed some anti-reflecting coating on a lens surface. So, once the design is fixed, then the perfect condition of 0 reflectivity would be valid for a single wavelength, but if we deviate from the wavelength, there would be some non-zero reflectivity. Okay. Now, till here what we considered is that there is a air and then there is a thin film on top of a glass, and this thin film is working as an anti-reflecting coating. But here we just considered 2 reflected light, but in interference part we know that the ray suffers multiple reflection and refraction, and therefore, here there will be lot of reflected light. Okay. And to have a better parameters for anti-reflecting coating, we will have to treat all these reflecting rays, we will have to take into account all these reflected rays. Now, in this part we will take into account all the reflections, and the effect of multiple reflection at the lower and upper surfaces results reflectivity of a dielectric film, that is given by equation number 8. Okay. If we take into account all the reflected rays, then the expression for reflectivity modifies, and the ultimate reflectivity turn out to be this. Okay. Here, as I said before, ray is coming, it is getting reflected from here and then from here again, then from here again. If we take all these reflections into account, then the reflectivity of dielectric film would be given by this expression. Now, here you see that we have a R1 term, R2 term, and there is a phase part del. The R1 is given by Na minus Nf upon Na plus Nf, while R2 is Nf minus Ng upon Nf plus Ng. From this expression you can see that R1 is reflection coefficient of the first interface of the thin film, R2 is the reflection coefficient of the second interface of the thin film. Yeah, because this is our glass, and on top of this glass this is anti-reflecting coating, and on top of this anti-reflecting coating we have air. So, this surface reflection coefficient is denoted by R1, while this surface reflection coefficient is given by R2, and the expressions for R2 and R1 are given here. R1 and R2, they represent the Fresnel reflection coefficients, and as I said before, and these coefficients are at first and second interfaces, and the phase del is nothing but this is our conventional phase 2 pi by lambda NFD. The 2 pi by lambda is nothing but k NFD is the phase, Nf is the refractive index of the film, d is the film thickness. Now, if you differentiate equation number 8, which is this equation, this is equation number 8. Okay. With respect to the phase del, we want R to be 0, R to be minimum. Okay. And mathematically, if we apply the condition of maxima minima here, then we can get the conditions for which R would be minimum. Okay. And for that we take first derivative of R with respect to del and equate it with 0, and upon equating we will get a condition which will lead to either maxima or minima. Okay. Now, if we equate the first derivative of R with 0, this gives sin 2 del is equal to 0. Okay. The first derivative of R with respect to del would be 0 only if sin 2 del is equal to 0, and indeed for R1 R2 larger than 0, cos 2 del is equal to minus 1 gives a minimum. Okay. Now, this condition cos 2 del is equal to minus 1, it represents the condition of minimum reflectivity, and when this condition is satisfied, the expression for reflectivity modifies, and the modified expression is given by equation number 11. Okay. The earlier expression was a bit cumbersome, which is given by equation number 8, and when you modified, when you put cos 2 del is equal to minus 1, which is the condition for minima, the new expression for reflectivity R is R reduces to R 1 minus R 2 upon 1 minus R 1 R 2 whole square. Now, if you substitute the expressions of R 1 and R 2 from these expressions, these are the expressions for R 1 and R 2, if you substitute them back into equation number 11, then we get this expression for R. Okay. Thus, for anti-reflecting coating, R is equal to 0 gives Nf is equal to square root of Na into Ng, because if you equate this to be 0 with 0, this is the Na Ng plus Nf square. This if you equate to 0, then you get this condition directly, Nf is equal to square root of Na Ng. It means even if you consider multiple reflection, still we will end up on the same value of Nf, which is equal to square root of Na into Ng. Okay. Or more generally, suppose we have 3 films of refractive index N1, N2 and N3, and if we want N2 to behave as a anti-reflecting coating, then N2 must be equal to square root of N1 N3. Okay. Now, the condition cos 2 del is equal to minus 1 gives that 2 del, which is equal to 4 pi by lambda NFD, this is equal to 2 m plus 1 pi, yeah, which is, and from here we can see the expression of D, which is the possible values of the thickness of the thin film, which will give 0 reflectivity. Okay. Now, reflectivity as a function of del is shown here. You see that if you vary del, then reflectivity vary periodically. It's a periodic variation is there. Okay. The maximum value of reflectivity is 0.04 and the minimum is 0. Okay. Now, whenever del satisfies this condition, we get a minima here. Okay. Now, this figure is drawn for Na is equal to 1 and Ng is equal to 1.5. R is maximum, that is 4% when del is equal to 0, pi, 2 pi, and the film is anti-reflecting when del is equal to pi by 2. Here the value of del is pi by 2, here the value of del is 3 pi by 2, here the value of del is 5 pi by 2, and so on. And the corresponding film thickness is given by these expression D is equal to lambda upon 4 Nf, 3 lambda by 4 Nf, or 5 lambda by 4 Nf, and so on. Okay. Then the question is now, can we use any of these thickness in making the anti-reflecting coating? Now, the answer is no, because if we pick the larger values of thickness, then what will happen is that, let us plot here the wavelength and here the reflectivity. Now, for larger value of D, say the minima is appearing at this point at some wavelength, okay, and this is for some D which is equal to D1, and let us pick another color, and this for this color let us draw again minima, and this is for D is equal to D2, and D2 is smaller than D1. Okay. Now, in this figure what you see is that for thicker thin film, the minima is very sharp, yeah, the D1 is larger than D2, okay, and therefore, for thicker thin film and thicker anti-reflecting coating, the sharpness of the minima is very large, minima is very sharp, okay, and as soon as you deviate from this value of lambda, say it is lambda naught, and if you deviate from lambda naught, the reflectivity rises very quickly, while for a smaller value of anti-reflecting coating, smaller thickness of anti-reflecting coating, a smaller value of d, you see that if you deviate from lambda naught, then the reflectivity is not rising very rapidly. The bandwidth over which reflectivity is minimum is large for smaller thickness of anti-reflecting coating, and therefore, people prefer the smallest possible thickness of anti-reflecting coating while designing the optical instrument. Hope things are understood. This is all for today. I end my lecture here. See you all in the next class. Thank you for joining me.